So in 6.3, talking about the unit circle, and we're talking about extending our knowledge of trig out beyond right triangles. So two really critical topics here in trig, and that are admittedly somewhat dense too. So I'll try my best to, explain as best as I can and give you the highlights, but this can be a really dense section. So we should start by talking about what the unit circle even is. Um, so the unit circle is an arbitrary circle. It's something that we've kind of just come up with on our own, with radius 1 and center at the origin. This circle can also be represented by the equation x squared plus y squared equals 1. And we use this as the basis for deriving trigonometric values for what we call special angles. And realistically, this can be extended for any possible angle, but when we're talking about trying to do things like this without a calculator, um, or when we first started working with the unit circle, say, we start with some special cases that you've seen before. So let's actually start by looking at some of these special cases. So if you look at the left here, you can see my unit circle, right? All of these points out on the circle are 1 unit away from the origin. So this would be the point 1, 0, this would be the point 0, 1, and so on. So let's consider some of these angles that we can draw in this unit circle, right? And every angle that I draw here, I'm going to draw counterclockwise from the x-axis. So I start at the x-axis, we have my initial side. We draw an angle out counterclockwise from that point to get to my terminal side, my ending side, and that's my angle that we call theta. So if I were to look at a 45-degree angle, obviously this is not drawn to scale, but if I were to start by considering my 45-degree case, well, let's try to figure out what we can learn from from this case. So I have radius 1 because every angle that I draw out, right, every point out here is 1 unit away from the origin, so this is radius 1. And if I were to drop a perpendicular line down back to the x-axis, I create my right triangle, right? And we'll call it x and y, two sides x and y. Well, you've probably learned in geometry that a 45, 45, 90 triangle, one of our special cases, is special because x and y are the same length, right? We know this probably from prior knowledge, from having taken geometry before. So I'm actually going to go ahead and call this x then, right? These are the same. So we can find the value of x by using the Pythagorean theorem, right? This is the right triangle. So, well, it would be 2x squared, right? X squared plus x squared equals 1. So x squared equals 1/2, and x equals 1 over root 2. Sometimes we like to rationalize this just because it makes things easier to work with, so we can call x 1 over root 2 or root 2 over 2. Well, this is great. Well, from this, we can actually come up with the lengths of my sides, which I've done, and we can also come up with the values for the trig functions at these points, right? So I can find sine of 45 degrees, which would just be opposite. So we know x is root 2 over 2 over hypotenuse, which is 1. So anything over 1 is itself. So sine of 45 is root 2 over 2. Cosine of 45 would be just adjacent over hypotenuse. So same principle, right? Root 2 over 2 over 1 would just be root 2 over 2. And tangent would be opposite over adjacent, right? So root 2 over 2 divided by root 2 over 2. Maybe I'll show it this time. Well, anything divided by itself is 1. So tangent of 45 is just 1. So here are kind of 3 angle measures that we can start to, or trig functions rather, that we can start to derive for ourselves. Of course, this would work with pi over 4 as well, because we know that pi over 4 and 45 degrees are equal. There we go. So that's our 45, 45, 90 case. We can do the same type of thing with 30, 60, 90. So we've learned in geometry from prior knowledge. First, we know that our radius is 1 because we're on the unit circle. And from our prior knowledge, we know that everything is done kind of relative to this short side, and since it's vertical, I'll just call it y. And since everything is done relative to our short side here, we remember from geometry that the hypotenuse is twice as long as the short side, and my other leg is equal to root 3 times the length of the short leg. So we've got our three kind of lengths just in terms of whatever the short side is, and this is actually still enough to figure out our trig functions. So we can find sine of 30 by taking opposite over hypotenuse and simplifying that to 1/2. And we can do cosine of 30 by taking opposite over, adjacent over hypotenuse and reducing that to root 3 over 2. And we can do tangent of 30 by taking opposite over adjacent and reducing that to 1 over root 3, which you might want to rationalize to root 3 over 3. All right, so just to kind of summarize what I've learned without the work, I'm just going to write it off to the side. Sine 30 is 1/2. Cosine 30 is root 3 over 2. And tangent 30 is root 3 over 3. The other special case, special angle that I care about would be 60 degrees. And we can actually just use the same triangle here because I've got the angle right there in my triangle. So following the same logic, that should be sine 60. Sine of 60 degrees is opposite over hypotenuse, which reduces to root 3 over 2. Hey, that looks familiar. I can do this with cosine. Get adjacent over hypotenuse, I get 1/2. And I can do this with tangent. I would get opposite over adjacent. And I would just get root 3. So to summarize what I've learned from that, sine 60, I keep doing that, sine 60 is root 3 over 2, cosine 60 is 1/2, and tangent 60 is root 3. So these three boxes that we've come up with so far, the 45's up at the top, my 30 degrees and my 60 degrees, and of course their radian equivalents, pi over 6, pi over 4, and pi over 3. We should know relatively comfortably to some degree, and actually a couple others that I'm going to go over as well, because it's going to make my calculations later on a lot easier if I'm pretty familiar with these functions and their values. The other two cases that I want to look at that are important are 0 and 90 degrees. And you might not consider being able to draw a triangle, but in trig we like to try to draw a triangle anyway. So if I were to consider a triangle whose angle down here opens up 0 degrees, just because that's where we're at, right? And it's a right triangle. Well, if I look back at my unit circle, right, if my angle doesn't come anywhere off of the x-axis, well, it's entirely length, right? There's no height. It's just the x-axis. So it still has a hypotenuse of 1 because the hypotenuse comes from the radius of whatever triangle I make in the unit circle. I said there's no height at all, right? Because it's not coming off of the x-axis. And it's all length. It's got a length of 1. So we can do the same process. I can find sine of 0, right? It's opposite over hypotenuse, which is 0. Cosine of 0, which is adjacent over hypotenuse, is 1. And tangent 0, which is opposite over adjacent, which is 0. I can do the same thing with my weird degenerate 90-degree triangle, because it's not degenerate because it's not really what we're used to calling a triangle, but it is, I suppose, in some sick way, a triangle. So if I look at 90 degrees, if I've opened up my triangle so that is all the way exactly lined up with the y-axis, well, there's no length at all. There's no measurable length at all. It's entirely height. So let's follow that same logic. The hypotenuse is still 1, always. There's no length, and it's all height. So let's apply my my formulas again. Opposite over adjacent, hypotenuse is 1. Adjacent over hypotenuse is 0. And opposite over adjacent is undefined because I'm dividing by 0 and can't do that. So in these boxes that we've just come up with are, I suppose, 15 really important functions or trig values that you should know. You should be loosely comfortable with these. If you can at least derive them for yourselves, that would be helpful. If you can happen to commit them to memory, that would be even more helpful and speed up the process even more. But the more comfortable you can get with those values, all 15 of those, the better. So whatever method you want to use for that is fine. There's a resource that maybe I can post that you can actually, there's a trick you can do with your hand to learn it and to figure it out. But moving on, because there is kind of a lot of information here, I want to talk about what's unique in the 4 quadrants of the unit circle. So if you remember from earlier in your prior knowledge, PK for prior knowledge, the XY plane has 4 quadrants starting in the upper right side. Quadrant 1, Quadrant 2, Quadrant 3, and Quadrant 4. So I'll label those up here too, just so we kind of have some connection here. Quadrant 3 and Quadrant 4. Well, if I consider what happens in each of these 4 quadrants, I discover some things about my trig functions. And the first thing that I want to start by establishing is that all of my trig functions have positive values in quadrant 1, right? If I considered my triangle in quadrant 1, well, there's a positive length here, there's a positive length here. The hypotenuse is always 1. So no matter what combination of sides I divide, I'll always have a positive value. If I consider a triangle that's out here, though, so if I consider an angle that extends into quadrant 2, which would be an obtuse angle, versus my acute angle in quadrant 1, well, if I actually consider dropping my perpendicular line and working with this triangle that kind of forms here, let me draw it out here, well, I now have a negative length, a positive height, and a hypotenuse of 1. So this would make my sine function positive and everything else negative. Right, opposite over hypotenuse gives me a positive number, but any other combination of sides I divide will give me something negative. Same logic applies down here. If I were to extend an angle out into quadrant 3, which is what we would call a reflex angle, so it's something that is greater than 180 but less than 360. Well, and I think about the triangle that I can make with the x-axis. I kind of, let's draw it out this way. All right, I have negative length and height and a hypotenuse of 1. So the only function that's going to be positive here is tangent. Everything else, meaning sine and cosine for now, is negative. Right? Opposite over adjacent, negative divided by negative is positive, and so on. And lastly, I can do this with quadrant 4 if I extend an angle out here, which would also be a reflex angle, and try to make a triangle with the x-axis. If I consider that triangle here, well, I've got positive length, negative height, and a hypotenuse of 1, so the only thing that will be positive here is cosine. And sine and tangent will be negative. So we've kind of picked up on 3 key things, right? If I kind of rewrite this, all functions are positive in quadrant 1. Sine, and we'll learn its reciprocal, will be positive in quadrant 2. Tangent and its reciprocal will be positive in quadrant 3. And cosine and its reciprocal will be positive in quadrant 4 and nothing else. So you have all, sine, tangent, and cosine. So if we think about this from quadrant 1 all the way around to quadrant 4, I like to remember the mnemonic device, all students take calculus. Or you can remember whatever other mnemonic that you want to use, but this is the one that's kind of stuck with me, to remember which functions are positive in each of the 4 quadrants. So all students take calculus. I started talking a little bit about making these angles with the axes, with the x-axis, and actually using the triangle that I would make from the x-axis up to that ending side of my angle. Right, we were focusing kind of on these triangles, these acute angle triangles. And those angles are important. That's what we call reference angles. Our IB calls them associated acute angles. And these angles are the angles alpha. That's a notation that I just kind of picked. This is the Greek letter alpha. Just I wanted to give it a symbol. And this is the angle that the terminal side of the angle theta makes with the x-axis. So if I look at my first example here, my 120 degrees, the acute angle I can draw with this ending side, this terminal side of the angle, would be this right here in purple. This we'll call alpha. And the distance from my terminal side down to the x-axis, well, if I went all the way out to this part of the x-axis, that's 180 degrees. So from 120 to 180 degrees, we'll put that in a different color in a minute, makes an angle of 60 degrees from the x-axis to the terminal side. Same thing with 330. If I think about the angle that takes me from the terminal side here up to the x-axis, this angle here would be an angle of 30 degrees. It makes an angle of 30 degrees from 0, or sometimes we call it 360, depending on the needs we need. From 330 to 360 is an angle of 30 degrees, so that's my acute angle. I can do this in radians also, so remember that instead of 180, I can consider this measure pi. This would be 0 and 2 pi. So the angle that I'm making is this angle back up to the x-axis, and this is an angle now of pi over 4. There's a really easy trick with radians. So the radian trick is that the reference angle alpha will always have the same denominator as theta, as whatever the original angle is. The reason why we use this is because the actual magnitude, so the actual number of sine theta or cosine theta or tangent theta, but I'm just using sine for an example, is exactly the same as the sine or cosine or tangent of the reference angle. But the sine SIGN of the result depends on the quadrant. Going back to my CAST, or my all students take calculus. So if I want to do sine 225, cosine 225, tangent 225, the first thing I should think about is the reference angle. So what's the quickest way for me back to the x-axis? So if I visualize this really quickly, 225 is going to put me out here. So the quickest way, so here's my theta. Here's my 225. My quickest way back to the x-axis is right here, this way. Here's my acute angle. This would be my reference angle. So what's the difference from 180 degrees to 225 degrees? My reference angle is going to be 45 degrees. So sine of 225 is at least going to be equal in number to sine of 45. But we know that in quadrant 3, if all students take calculus, so tangent will be the only positive function. So my sine will be negative. Makes sense, right? So I know that sine of 45, we learned way back up here, sine of 45 is square root of 2 over 2. So sine of 225 is going to be negative square root of 2 over 2. Same logic applies to cosine. Tangent's the only positive function right here in quadrant 3, so this will be equal to negative cosine 45. And we learned before that cosine 45 is root 2 over 2, so this will be negative root 2 over 2. And finally, tangent 225 is going to be exactly equal to tangent 45 because tangent is positive in quadrant 3 always. And we learned before that tangent 45 is 1. So this is why it's important to know these reference angles. It speeds up your calculation a lot. The last thing I want to go over in this video is this last problem here. So if cosine theta equals root 3 over 2 and tangent is negative, find theta and find sine theta. So let's just figure out where I am right now. I know that cosine is positive and tangent is negative. So it tells me that cosine is going to be the only positive function, so this puts me in quadrant 4. But, so I know that cosine theta is root 3 over 2. But I also know that whatever that reference angle, that whatever angle I have here, right, here's my angle, but here's my reference angle, makes with the x-axis, cosine of that reference angle will also be root 3 over 2. So if I look backwards and kind of look back at all the information I've come up with before, out of all my information, where's cosine root 3 over 2? And that would be right here at 30 degrees. So I'm starting with my associated acute angle, oh, there it is, because it gives me the information I need to know. So cosine alpha is root 3 over 2 when alpha is 30 degrees. But I'm in quadrant 4, so what big angle, obtuse or reflex angle, makes a reference angle of 30 degrees? Well, if I kind of work it backwards from the x-axis being 360 and I go away 30 degrees, I'm sitting here at 330 degrees. So this tells me that theta is 330. So we know that sine of 330 is going to be negative sine of its reference angle, which we've learned is 30. And we've learned from before that sine 30 is 1/2. So sine 330 is negative 1/2.